Right, we are in the middle of a calculation. Unfortunately, I had to break at a somewhat inconvenient point last time. We are discussing bound orbits, and we began with remembering what we probably already knew about circular orbits. Let me just do this again in terms of, this is actually no other axis. Let me explain this just in terms of a picture. Here we have our radius coordinate. Here's a singularity at r equals 0. Here is rs. Here's 3/2 rs. And here's 3 rs. And what we have seen is that in this domain, between 3 rs at infinity, we have stable circular orbits. This is a so-called ISCO, innermost stable circular orbit at r equals 3s. Beyond r equals 3s, at 3 rs, we have still circular orbits, but they are unstable. So here we have unstable, hope you can read this, circular orbits. And here in this domain, we have no circular orbits at all. So r equals 3/2 rs, that's a light sphere about which we will talk a little later again. But I think most of you know already that if a free particle wants to move at the radius with this constant value, then it would have to move at the speed of light, which of course is impossible, and that's the reason why the circular orbits exists only above 3/2 rs. Just to make this sure, in this domain between the horizon and 3/2 rs, it is still possible to orbit if you have an engine. Yeah? We are here talking, when I say orbit, I mean orbit of freely falling particle. So you give the particle an initial velocity tangential to the radius, and you want to do it in such a way that it stays on this radius, just under its own free motion. And this is possible only up to this line. If you have an engine, and if you fire it, and then you drive yourself around the circle, this is possible in this area. It's not possible here, because there the arc coordinate has to decrease. Yeah? So for a material object, for something which cannot move at superluminal speed, it's impossible to stay at a constant radius here. But it is possible here. Okay, so this was what we learned about circular orbits, and I will come back to this soon. I will need this result. And then we talked about bound orbits in general, not necessarily circular. And for that we had our effective potential, which was labeled by the constants of motion E and L. It was a function of r. And it was introduced in such a way that along each orbit we have the equation dr by d phi squared with a factor 1/2, just for a convention, plus VEL of r 0. So you see the allowed regions are the region where the potential is negative. Yeah, and the turning points where dr by d phi is 0 are the points where this is equal to 0. And the shape of the potential, if you want to have a bound orbit, it was necessarily of this form. So we must have 3 zeros, which I labeled R0, Rp, and Ra. Ra, the index A, stands for apocenter, or whatever your central object is. So if it would be the sun, then you would call it the aphelion, and the P stands for pericenter, or perihelion if the center is the sun. And the last thing we did was that we expressed these zeros, actually not only these two, but here's the bound motion. Here the bound motion is in this area. So you see the potential must be negative if this equation is to be satisfied. So that's the case here. And these are the turning points where this becomes 0, because this becomes 0. So what we have here is an orbit which oscillates between these two boundary values. It oscillates periodically with a maximal speed here just in the middle, where this function reaches its minimum. For the same potential, we also have a plunge orbit here. Yeah, that would be an orbit which reaches the maximum at RO, and then falls into the singularity. But we are not interested in this. We are talking about bound orbits. And we express these zeros in terms of the semilatus rectum and the eccentricity, which is always convenient. So we wrote Ra in the form P. This is a bigger one, so I must have one minus E. And Rp in the form 1 plus E. Yeah, so for an ellipse, if you just think of an ellipse, these are not ellipses what we are talking about, but you could apply the same substitution also to an ellipse, to a Kepler ellipse. Then we have here Ra, here Rp, and this would be the semilatus rectum P. And the E is the eccentricity. So obviously the E is 0 if and only if Ra and Rp are equal. And the crucial thing which we calculated, this was the last thing we calculated last time, was that also the Ro can be expressed in terms of P and E. This was what we found last thing. It was, what was it, PRS divided by something? Let me look it up. PRS divided by P minus 2RS. So actually the E doesn't occur in this equation. But in any case, it's possible to express also Ro in terms of these two parameters. So you could label the orbits with E and L. That's what you began with, two parameters, E and L. They are not immediately associated with a geometric interpretation. Well, we know if L is equal to 0, then it's radial. That you can recognize immediately. But otherwise, the values of E and L do not translate immediately in geometry. As an alternative to using E and E, you could use Rp and Ra. That's very geometrical. Yeah, it's a pericentral radius and the apocentral radius. And as a third alternative, you could use P and E. You just reparameterize the orbits in this way. And mathematically, this is by far the most convenient way. The equations become most convenient if you use P and E. It's very often used in when you deal with orbits, Newtonian or general relativistic or whatever. And what we want to discuss now, on the basis of these observations, is what are the allowed values for P and E, for bound orbits. Just for the sake of comparison, let's call Newton. This means the Kepler orbits. Well, I think everybody knows what the bound orbits are in the Kepler potential. If we plot it in a PE diagram, first of all, we observe that E, of course, must be smaller than 1. Yeah? We want to have a finite apocenter, so this must be smaller than 1. E equal 1 is, in the case of the Kepler potential, we have ellipses. The bound orbits are ellipses, and E is the eccentricity in the usual way of an ellipse. And if E becomes 1, then the ellipse becomes more and more stretched. And you see Ra goes to infinity. Yeah? So this corresponds to the limit where the ellipse becomes a parabola. And all values here 0, all values between 0 and 1 for E, and between 0 and infinity for P are allowed. So this whole rectangle is where we have bound orbits. Yeah? In the Newtonian theory, in the motion, for the motion in the Kepler potential. So here, of course, we have the stable circular orbits. Yeah? E equals 0 means we have a circular orbit, and they must be stable because they are in the neighborhood bound orbits. Yeah? This means we have a stable circular orbit, and they are possible for all radii between 0 and infinity. If E is 0, then P, of course, is the same as a radius. Yeah? If E is 0, then you see Ra and Rp. Just gives the radius of the circular orbit. So that's the Newtonian case. And now we want to discuss this for Schwarzschild geodesics. We already know that the stable circular orbits do not go down to R equals 0. So they end here at R equals 3RS. So you would expect that also the rest of the figure would not extend to R equals 0, to the singularity. And that's actually what we want to find out. We want to see where we have the boundary here in this diagram. So now we talk about Schwarzschild orbits. And yeah, how do we find out which are the allowed values for P and E? Here we have the diagram. So you have to see what are the limiting cases where the shape of this potential goes over into a different shape where we do not have bound orbits. And obviously there are two limiting cases. The first limiting case is when Rp and Ra coincide. Yeah, if you play around with the parameters in such a way that Ra and Rp come closer together, and the limiting case is when they coincide. If you go beyond this, you don't have a bound orbit anymore. And the other limiting case is when Ro and Rp approach each other. So the first limiting case, and let me begin with the one which is easily understood. That's the one when Rp and Ra come close together. So when Rp becomes equal to Ra. So then the diagram looks like that. So it always comes out of zero with a tangent which is pointing downwards, because the derivative of the potential at zero was minus Rs or something like that. And then it goes up. And now we have this limiting case where it just touches the axis. So here we have Rp equal Ra, and here we have R0. Well, and what is this? Well, obviously, this is a stable circular orbit here. Yeah? Here's a stable circular orbit. Why is it stable? Because if I perturb this a little bit, then I get a bound orbit. Yeah, then the minimum goes below the axis, and then I have a bound orbit. So this is a stable circular orbit. So this is one of the boundary curves, stable circular orbit. One of the boundary curves of our region. For the Schwarzschild case, so we want to plot the analog of this diagram. So we have again here E, we have again here the simulatus rectum, and now we already know that certainly it will not go beyond E equal 1, because then the apocenter would not be defined. And now we see that one boundary of the region is this here, and it goes up to 3 Rs, which is the ISCO. Yeah? Because this is where we have, these are the parameters for which we have stable circular orbits. We have discussed this last time. That's why I recall this result. So this is one of the boundary lines. And what we have to find out, what is here? What is the boundary here? And for that we have to consider the other limiting case, when R0 or RO or whatever you call it comes together with Rp. And that's more interesting actually. This is not so, it's not so obvious to see what this geometrically means. RO is Rp. Let me draw the graph. Then it goes down here, then it touches the axis and goes up here. Here we have the apocenter, and here we have now Rho equal Rp. Now what is that? Here we have an unstable circular orbit. Yeah? Because if I perturb this a little bit, then I have no orbit at all in the neighborhood. Or I have one which goes down to the horizon and then to the singularity, or it goes far away. So this is an unstable circular orbit. Oops. I think I need more space. And then, well, remember, the allowed region for an orbit is a region where the potential is negative. Where is the potential negative? Well, it is negative here. So here a particle can move. Yeah? And what does it do? Because here the velocity becomes zero with a horizontal tangent. Yeah? It becomes slower if it approaches this point. So it reaches this point only asymptotically. And this is true for the future and for the past. Yeah, so what the particle does, it spirals away. Always remember, I just plot the r coordinate. There's also the phi coordinate which goes around, yeah, independence of this parameter L, of this which is the angular velocity. So the particle spirals around, and the radius coordinate is increasing very, very slowly because this here is very, very small. And then it reaches the dr by d phi reaches its maximum here. Then here's a turning point. So the particle goes out, reaches the maximum radius, and then turns back and spirals back. So it spirals back towards this unstable circular orbit. So it starts asymptotically in the past at the unstable circular orbit, and it returns to the same unstable circular orbit for t to infinity. And such an orbit, which starts and ends at the same limiting orbit, is called homoclinic in Greek. So that's what we call a homoclinic orbit. So that's a word which you find quite generally in the literature on dynamic of systems, not just on geodesics. So here in the Schwarzschild spacetime we have a homoclinic orbit. There's also the notion of a heteroclinic orbit. That's an orbit which starts at one limit equilibrium point. Yeah, you might say this is an unstable equilibrium point of this potential. So which starts at one equilibrium point and ends at another, at a different equilibrium point. That's what they would call a heteroclinic orbit. In the Schwarzschild spacetime, heteroclinic orbits do not exist. But they do exist in the Schwarzschild spacetime with a cosmological constant. That's a so-called Kotler spacetime, or Schwarzschild de Sitter spacetime, and I think I will later briefly touch upon this. So then we will also have heteroclinic orbits. Here in the Schwarzschild case, we have only this homoclinic orbit. And then there's another orbit here, but this is not interesting for us. This is this here. So what is this? This starts spiraling asymptotically at this radius. Then the radius coordinate becomes smaller, and it ends up in the singularity. So that's again a plunge orbit which starts asymptotically at an unstable circular orbit. But these things, these homoclinic orbits, they are really interesting, and that's a new feature. That's something which in the Newtonian case doesn't exist. Yeah? That's a new feature which occurs in the Schwarzschild spacetime, and it occurs, for parameters where unstable circular orbits exist. And we know already where this is. This is this region here, in this region. So these are the values which are allowed for the limiting circle. Yeah? So they are close to the horizon.
Won't the particle eventually fall into the black hole? I mean, this is an unstable circular orbit, and the particle can go either way. So.
From here, you mean? So this is unstable. Yes, that's true. And what I just tried to explain is that there are two orbits which start asymptotically at this circle. One goes in the direction of increasing r, reaches a turning point, and comes back asymptotically, and the other one goes in the direction of decreasing r and falls into the black hole. So it ends up in the singularity. Yeah, it crosses the horizon and ends up in the singularity. Was this an answer to your question?
That returning particle from some finite radius is RA.
This here, yeah.
When it comes back, can't it then after it reaches R0 go to singularity?
Okay, this particle, which has a turning point here, never arrives at R0. Okay. It goes asymptotically towards this radius. You always have to think of the phi coordinate. So what this particle does is it reaches the maximum, then the radius coordinate becomes smaller, but asymptotically. Yeah, it approaches a limit circle, and it never reaches this circle. That's a circle at R0 equal Rp. So it cannot cross this. So you cannot have a particle which goes this way. That's impossible. Yeah? Because here it has speed 0. Yeah? The r by d phi is 0 according to this equation here. So it cannot cross this point with a finite velocity. It can only approach it asymptotically. Okay, so the homoclinic orbits give us the missing boundary here. So we need to calculate where they are. And they are at parameter values where it is written R0 is equal to Rp. So let's evaluate this equation. R0 is Rp. What does this mean? Well, we have the expressions for R0 and for Rp here. Rsp divided by P minus 2Rs is Rp was P divided by 1 plus E. I think I can evaluate this equation. So this means Rsp times 1 plus E is P times P minus 2Rs. I can cancel the P, and if I write everything on the right hand side, then I have P minus, that's 2, and another one, that's minus 3 Rs, and this comes to the other side, minus Rse is 0. That's the equation for this boundary curve. So that's the relation between P and E, which must hold along these homoclinic orbits. And now we can draw the picture. I think I should do this a little bit larger because I want to indicate a lot of things in this picture. So here I have E, here I have P. Interesting things happen at 3Rs. Here's 1. So we know already this is a boundary and this is a boundary. And now we have found the third boundary, this equation. Where does it meet the axis? If E is 0, P must be 3Rs, so it starts here. Yeah, this line starts here. And if E is equal to 1, then P must be equal to 4Rs, right? And that's the equation of a straight line. Yeah, it's a linear relation between P and E. So if here is 4Rs, it must arrive here, and it must be a straight line. So that's the curve where we have the homoclinic orbits. And the bound orbits are here. The bound orbits are in this region. So this region is forbidden for bound orbits. Yeah, these values of P and E are forbidden for bound orbits. So just to remind you, here we have the stable circular orbits. Here we have the homoclinic orbits. Yeah, and here we have unbound orbits. Yeah. If E, that's the reason why I draw this here. Well, it's also a limit. Yeah, it's also a limit. Maybe I should write it, do it in this way. So neither this line nor this line can actually reach by bound orbits. Bound orbit means a thing has an Ra and an Rp, and both are finite. Yeah? And that's not the case for any of the orbits on the boundary. It's true for this one, for these ones here. They have an Rp and an Ra which are equal. Yeah? But they don't. These orbits do not have an Rp, because they only approach the Rp asymptotically. And these orbits here don't have an Ra, because Ra becomes infinite if E is equal to 1. Yeah? So this is, that's the diagram. And we can talk a little bit about what's going on near this line of the homoclinic orbits, which is also called the separatrix. Yeah, the name refers to the fact that it separates the domain where we have bound orbits from the domain where we do not have bound orbits. Yeah, that's what meant by this name. So the separatrix starts here. So what is this? This is the ISCO. Yeah, the innermost stable circular orbit. What are these points here? Well, let's talk about the other endpoint first. What's the other endpoint? It has a P of 4Rs. And an E of 1. So this orbit has an Rp in a limiting sense. It reaches this only asymptotically. What was it? P divided by 1 minus, Rp is P divided by 1 plus E. 4Rs divided by 1 plus 1 is 2Rs, right? So this approaches a minimum radius of 2Rs. Hey, wait a minute. That's not the limiting case for the unstable circular orbits. So the unstable circular orbits go down until 3½ Rs. So these homoclinic orbits, the limiting curve for the homoclinic orbits end already here. So they are only in this domain. Yeah, they don't go down to the to the light sphere. And what's the RA? Well, in the denominator I have 1 minus E, and if E is 1, then this becomes obviously infinite. So that's an orbit which asymptotically approaches infinity in one direction and asymptotically approaches 2RS in the other direction. And in between we have homoclinic orbits which have minima, a minimum radius, a pericenter, which they approach asymptotically bigger than 2RS and smaller than 3RS. And they have apocenters, which where they have turning points between between infinity and 4RS, right? So that's the situation. And well, if we have a geometric understanding what these homoclinic orbits do, then I think we also have an understanding of what orbits do which are close to homoclinic orbits. So let's say this orbit here. Yeah, this has an E, which is very close to 1. So it means it goes very far out. Yeah? If E is close to 1, this means RA is close to infinity. But on the other hand, it is close to the separatrix. It's close to a homoclinic orbit. This means it has a pericenter, which is very close to one of these unstable circular orbits. And the unstable circular orbits are very deep down, very close to the horizon. Yeah, close to 3RS or something like that. And near 3RS, the particle makes many, many turns, because if the point would be on the separatrix, it would make infinitely many turns. It would approach this infinitely. So if it's close to the separatrix, it makes many, many turns. So what is this orbit doing? It goes out to a very big radius, then comes back and makes many, many, many turns near a small radius. And it goes back again, very far out. Turns back, makes many, many, many turns. And that's what is called a zoom whirl orbit. So here this shaded region is a region of zoom whirl orbits. Yeah? They are zooming out, they are going out too far, to radius values far away, and they whirl around a radius coordinate close to the black hole. And that's a feature, of course, which is completely unknown in the Newtonian celestial mechanics. Yeah? So Newtonian mechanics, as in the Kepler problem, we just have these boring ellipses. Yeah? And you might think that if you do general relativity, what you do usually in a course on GR when you study Schwarzschild, you discuss a perihelion precession. And then you get the impression, well, you might get the impression, the only thing that happens is that now these ellipses start rotating a little bit. Yeah, they have this precession. But if you go in the strong field regime, in the highly relativistic regime, where you are close to the horizon, then completely new features occur. Yeah, so the orbits are very, very far away from Kepler ellipses. They have no similarity with Kepler ellipses. And the most interesting phenomenon are these zoom whirl orbits. Actually, the zoom whirl effect is much stronger in the Kerr spacetime. We will come back to it. So here you can calculate how many turns these things are doing if they go out to a certain radius. And you can have much stronger effects, it means much more turns for particles which do not go out so far in the Kerr spacetime when the black hole is rotating. And the faster it is rotating, the stronger the zoom whirl effect becomes. So that's something which we will come back to later when we talk about the Kerr metric. And we will also come back to a similar diagram when we include the cosmological constant, when we do the Kotler spacetime. And the picture also becomes a little bit more complicated, because then we also will have a border on the right hand side. Here it is, if you are far away from, if P is very, very big. Yeah, P, the simulatus rectum, is very big. This means the orbit goes, we are in the regime where the Newtonian approximation isn't too bad. Then, we have a situation which is similar to what we know from Newtonian physics. So the interesting things only happen here. in the highly relativistic regime. With a cosmological constant, also the Newtonian limit will be modified. Yeah, so far out to the right, we will have interesting things. As a question?
Have these zoom world orbits also found in space? Examples for these?
Sorry, I didn't get this.
In space, did astronomers find a zoom world orbit?
Whether they exist in nature? No, I don't think so. I don't think that we have really clear evidence. Where there are theoretical investigation of what's going on in the accretion disk around black holes. But I think this phenomenon has not really observed in features of accretion disks. So when we're talking about particles orbiting a black hole, and close to the black hole, then this would mainly be matter which is rotating around the black hole, in the form of a disk or in the form of a corona or something like that, or maybe in a jet which is ejected by the black hole. And there are models for the dynamics in particular of the accretion disk, which is more or less exclusively based on the radiation we get from these objects. Yeah, what else do we get? And if we study these, then we can try to look for features which could come from this kind of orbits. Well, actually, we are talking about geodesics here. So if you say that the particles in an accretion disk move on geodesics, you ignore a lot of things, right? You ignore the pressure in the accretion disk. You ignore the effect of magnetic fields if you have charged particles in a plasma or something like that. So it's an idealized situation, but you can study theoretically then also phenomena of this kind. But as far as I know, one hasn't found really an observable feature which could be directly observed with these zoom world orbits. Actually, I mentioned several times, and you probably knew already before, that at the moment one of the most pressing questions of one of the most pressing questions in general relativity is direct detection of gravitational waves. And for what objects do we expect to see gravitational waves? Well, one possibility is that you have a black hole and a much smaller body inspiring towards the black hole. That's what is called an EMRI, E-M-R-I, extreme mass ratio inspiral. Yeah, you have a very small, in comparison to the black hole, small body which approaches the black hole. And then you can approximate the orbit of this body by a geodesic. Yeah, if the things have approximately the same mass, then you can of course not approximate one by a geodesic in the field of the other. But if one mass is much smaller, then this is reasonable. And you might expect that something like that occurs. Yeah, so that a particle which moves around a black hole is in such an orbit. And you can look for the gravitational wave signals which are associated with this kind of orbits. So in this sense, one tries to make contact with observations. But until now, we haven't found any gravitational wave signal. So for this reason, we also haven't found any signal which comes from a zoom world orbit. But this is something which might happen in the near future. Yeah? There was a question?
Yeah, you said that there's like a corona around a black hole.
That's one possibility, yes.
Like jets or something. So it's pretty much like stuff that's happening in the sun, or around the sun, happening at a black hole as well.
Yeah, so the question was about the analogy between what's going on around a black hole with an accretion disk, a corona, or a jet, the similarity with the sun. Well, the sun has something which is called a corona, but it's a different kind of corona. Yeah? And the sun, to the best of our knowledge, does not have an accretion disk. We're fairly sure that it has not, and it certainly has no jets. Yeah? So these are more dramatic effects. Also, well, it's not clear that every black hole has all these dramatic features. So for instance, for the black hole at the center of our galaxy, we are fairly sure that it has an accretion disk. There's also some evidence that it has a corona, a more or less circular component. But the people are still fighting with each other if there's a jet. There's a group of radio astronomers who say, yes, there's a jet, and there's another group who say, we see absolutely no evidence for a jet. Yeah? So this is something under debate. We don't know it. But there are other black holes for which we are absolutely sure that there is a jet. For instance, M87 has a huge jet. Yeah? It's the most characteristic feature of the whole galaxy, that there's a jet coming out of the center. Okay. So that was what I wanted to say about the zoom world orbits. Now I have 10 minutes. So should I start with, so the next section, and this would actually be the last section on the Schwarzschild spacetime, would be on light-like geodesics. I will speak a little bit about lensing by a Schwarzschild black hole, in particular on the shadow of a Schwarzschild black hole. I'm not sure if it's reasonable to begin in 10 minutes with this. Maybe there are more questions? That would be...
So is it reasonable to expect that the stars orbiting the black hole in the center of our galaxy could have these zoom world orbits or not? I mean,
well, the zoom world, the question was if it's reasonable to assume or to conjecture that zoom world orbits occur near the black hole at the center of our galaxy. Every black hole, if it is described by the Schwarzschild spacetime, admits these orbits. The question is there a particle coming in which do us a favor to enter exactly on such a kind of orbit? And at the moment I don't see any reason why this should not happen. Yeah? We do the orbits which we can really observe, where we see individual stars which move on orbits around the black hole at the center of our galaxy. They are at very, very big radii in comparison to the Schwarzschild radius. Hundreds or thousands of Schwarzschild radii. So these are these infrared stars which we actually observe since the mid-90s. So we follow the orbit of a couple of stars around the center of our galaxy since about 20 years now. And the orbits are Kepler ellipses, to the best of what measurement can do. We do not see any deviation from a Kepler ellipse. So they can be described perfectly well in Newtonian terms. So the relativistic effects are negligibly small. There are now new instruments being built, in particular with a very large telescope in Chile. They are building a new infrared instrument for this, which is called Gravity. I think it will go into operation next year or so, and they hope to zoom in more closely to the center of our galaxy with this instrument. So maybe then there's a chance that we observe objects which orbit the black holes at closer at a smaller distance, and then the relativistic effects certainly will become relevant. So the people who are working on this instrument are quite confident that they will find orbits for which the relativistic effects can be observed. If they actually will find something like a zoom world orbit, okay, we do not know. Yeah? And there's also I will come back to this thing at the center of our galaxy when I talk about lensing. Of course, there's strong effort now to observe light closer to the center of our galaxy, and to see something which is called the shadow of the black hole at the center. And this would also be then something which happens very close to the horizon, a few Schwarzschild radii away from the horizon. But at the moment we cannot look so closely towards the center of our galaxy. And to say this again, this won't work in the optical. There's no chance to see anything in the optical because there's a lot of dust around the center of our galaxy. So with optical telescopes, you will never see anything about the center of our galaxy. So it works in a certain window in the radio range. It works in particular in the infrared. So most of the observations I was talking about are in the infrared. And it works in the X-ray. So we also have information on X-rays coming from the center of our galaxy. There the resolution is not very good. Yeah? So with radio telescopes we reach a resolution of 20 microarcseconds or something like that now. With X-rays we are far away from that, orders of magnitude. So we do not have this good resolution. So I was carried away. What exactly was the question? Had I answered the question? Okay. Any more questions?
I have a question. When we consider those separatrix, to which scale can we actually observe those? I mean, when we go to the top two equal to 1, then I assume it would be some kind of orbit which goes to infinity, so it takes infinitely long to arrive there. But I know also in the solar system there are some smaller orbits. So what is the extremum we till now observed?
Okay, yeah, that's an interesting question. The question was to what extent these orbits on the homoclinic these homoclinic orbits on the separatrix are actually associated with orbits which, at least in principle, could be observed in nature. What we are doing here is we have a model where we have an object at the center and no other matter. Yeah? So we have an isolated object. The space-time asymptotically is flat. So any cosmological influence is completely ignored. So if we go very far away from the center, then this model will not be useful anymore. Because then if I extend my solution of, let's talk about the sun. Yeah, we apply the Schwarzschild solution to the sun. It's a very good model for this, but not up to r equal infinity. Yeah, at some point we will meet Proxima Centauri, our next neighbor, and certainly then this metric is not the right thing for describing the space-time, right? And for this reason, you are perfectly right. Orbits which go out to very big radii are actually not realistic. They have nothing to do with things which are observable. So yeah, you might ask for the black hole at the center of our galaxy, up to what radius this is a reasonable model? Well, certainly up to the radius where these stars move around, which we observe. Yeah, because there's a description, the mathematical description fits perfectly well the observation. So let's say a few thousand Schwarzschild radii, I would say. Yeah. So for this, it's certainly a good model. Any more questions? Then I think we stop here. I say goodbye to everybody who is watching the recording, and we go over to the tutorials.